hi, I'll be just briefing you the problem statement. So without any further delay, let's start. So basically, they are you are given an array of size n, and you have to perform some sort of computation and find the answer for each query. So there are certain queries that you need to answer. So each query you will be giving two ranges. So let's say this is a range and this is a range, and you will also given an integer k. So basically this is L1 and this is L2 and this is R1 and this is R2. So this is basically the range 1 and this is basically the range 2. So what they are just trying to say is, let us consider any element present in this range 1. Let us say this to be as I, and let us consider any element with present in the range 2, and let's say that is to be j. And if we perform the XOR operation on this, and the resultant should be equals to 1, you need to find how many such I comma j pairs exist. So that is what the query says, and the similar kind of queries are actually asked, and you need to answer each query. So for each query you are given a k, and you are given two ranges, and you need to pick an I comma j where I belongs to the first range and j belongs to the second range, such that I performing the XOR operation on I and j should be equals to 1. See, XOR of I and j is equals to 1, which determines that uh, uh, let me correct you, XOR of I comma j of kth bit. So my bad, I just forgot to say this. So take an take an element from this range 1 and take an element, let's say j, from this range, and if you perform the XOR operation of kth bit of I and kth bit of j, then this should be equals to 1. So what does that mean is, the whatever element that you have taken from this element, its kth bit is different from the element which is taken from this the kth bit of this element that has been taken from this range. So more specifically, if I would say, the kth bit of I is different from kth bit of j. So that is what they are just trying to say. You need to find how many such I comma j pairs exist. So how can we find this? So one simple way is, find the count of numbers present within the range such that whose kth bit equals to 1. So let's call it to be cnt1. So cnt1 we define cnt1 in such a way that the count of elements present within this range whose kth bit is equals to 1. So we will also define cnt2, which defines that number of elements present in this range R2 whose kth bit equals to 1. So how this will be useful to find us, we'll be just seeing now. And let's say the size of this range should be n1 and the size of this range to be n2, which is equals to r1 minus l1 plus 1. This is the number of elements present in this range, present from l1 to r1, and this is r2 minus l2 plus 1. So this is the count, and this is the total size of the two ranges. This is range 1 and this is range 2. Yeah. Now what can we do is, let's say count one, let's say we have two elements whose indices are like, let's say 3 and 4, or like let's take three elements whose kth bit equals to 1. Fine. So this is just an example, this might not be true, but for now let us take this as an example, and let's say this to be, there are two elements whose kth bit equals to 0, like let's say k1 and k let's say 4 and 7. No, we should take some different elements, 10 and 11, let's say. See, these examples might not be correct, but I'm just trying to say you the solution. So let's say this kth bit of this number is actually 1, and kth bit of this number is actually 1, and the kth bit of this actually number is actually 1, and the kth bit of this number is 0, and the kth bit of this number is 0. If we XOR these two, kth bit of this number and this number, we will be getting 1. Since the kth bit is 1 and kth bit is 0, and we know that XOR of two different 1 and 0 is actually 1. So we can take this 3 with any of these two. So we have two chances plus, and we can also take this 4 with any of these two. So which will be again 2, and we can also take this 5 with any of these two, which is again 2. So which is equals to 2 into 3, like which is equals to 3 into 2. So what I'm just trying to say is, why did I say this? Because let's say the count of ones kth bit is equals to 1 is CNT1, and let's say the count of zeros, like the count of numbers in the range R2 whose kth bit is equals to 0 is which will be equals to N2 minus CNT2. So this is the count. If you multiply these two, those are the possible outcomes, the desired required number of pairs of I, Z. If you multiply this, just we have seen before. So this is one possible answer. So count CNT1 into N2 minus CNT2, and other possible answer will be, we'll be taking the number of elements whose kth bit equals to 0 with number of elements whose kth bit equals to 1 in the second range, first range and second range respectively. So number of zeros in the first range will be, whose kth bit equals to 0 in the first range will be N1 minus CNT1, and what is the number of elements whose kth bit equals to 1 in the second range will be CNT2. So if you want to find the total possible outcomes, and we should be multiplying these two. So these two cases can be possible. So the total number of possible pairs of I, J will be 1 plus 2. So this is the answer that we need to find. How can we find that? Now let's get into the implementation part. How can we do this? One kind of way is, for every query we can traverse within this range and check if this let me write down. So check if ARR of I and 1 whether the kth bit of ARR of I is equals to 1 or not. So this is one of the way, and with this traversing from L1 to R1 and writing this if statement, you can actually find the number of elements CNT1, and similarly for CNT2. So what happens is, you will be giving a lot of queries. You will be giving Q queries. So find every time if we calculate these things, will be taking a lot of time, and which will be O of n square, which will leads to time limit exceeded. So we need to optimize this. So how can we optimize this thing is the actual task of this problem. So how can we do that? So what we are just trying to do is, this is kind of prefix sum problem. So we need to pre-compute the result. What I mean to say is, let me say, yeah. So what I'm just trying to say is, from every index up till this index, like till this index, let's say this is 0 index, 1 index, 2 index, till ith index will you calculate all the count of 0th bit, 1th bit, 2nd bit, 3rd bit, 4th bit. Like what I'm just trying to say is, till ith index we will calculate number of elements whose 0th bit equals to 1, and we'll also we'll calculate number of bits whose first bit equals to 1, and number of elements till I whose second bit equals to 1, and so on till how many bits we should be calculating is, see, the number of bits will not exceed 65, something like I think that will be taking around 62 given in the constraints. So I'll be just taking till 65. That really doesn't make sense, doesn't make more difference. Yeah, I will be calculating for every ith index number of elements till ith index whose 0th bit equals to 1, first bit equals to 1, second bit equals to 1, third bit equals to 1, fourth bit equals to 1. We will be calculating this for every ith index. So what is the use of this is, whenever if we want to calculate for this range, let's say we want to calculate for this range, what we'll be doing is for any kth bit, so we'll be having the number of elements whose kth bit equals to 1 till ith index. For example, this is the R and this is L. We'll be having the count of elements till R whose kth bit equals to 1. If we subtract from this, if we subtract, let's say this is C1, count of elements whose kth bit equals to 1 till R, let's say this is C1. If we subtract C1 minus number of elements whose kth bit equals to 1 till L minus 1, let's say this is C2, then we will be actually getting the number of elements whose kth bit equals to 1 within this range. So we'll be computing this before running the queries, and for each query this operation is actually a constant time. So in this way we can optimize the time. So for each query we'll be just do this operation till this minus this, we'll be getting within this range how many bits are actually taking place. So that is what the main logic is. So how we'll be doing this is now we'll be just saying now. So let's get into the code part, so you'll be understanding in more better way. So we are taking n, which is basically size, and q, and we are taking the vector, we are declaring it to be n plus 1 as size, and we will be taking as 1 based index. So this is the pre-computation array. So what this defines is, we'll be taking for vector of vector. What this says is, we have n plus 1 index. For each index we will be finding, for each index we have a vector of size 65, which defines till ith index number of elements whose first bit equals to 1, whose second bit equals to 1 till 65. So in fact what I am just trying to say is, so we'll be having 0 0 0 0 0 till 65. So this is for 0th index, and this is for first index, and this is for second index, and this is for third index. So what we'll be doing is, for till 0th index, number of bits whose 0th bit equals to 1, this is the count of this is the count of this, and this is the count of elements whose first bit equals to 1 till 0th index. So I think you got the idea. Let's define for this. See, number of elements whose 0th bit equals count of number of elements till the index 3 whose 0th bit equals to 1. and this defines number of elements till 3 till third index whose first bit equals to 1, and count of elements till 3 whose second bit is equals to 1. So this is what this matrix says us. So I hope you are understanding. So we have taken since it is one based indexing, we are taking the zeroth count of till 0 to be 0 for all the 65 bits, and from 1 to n will be now calculating till ith index how many count of each bit, like how many elements, how what I'm just trying to say is how many element will be taking the first index, and we'll be taking the index present element present at ith index. And if the let's say initially we start with 0th bit, if the 0th bit contains 1, then we'll be adding the frequency of that kth bit by 1. We'll be incrementing it by 1. If it is not, then we'll be just going to the next bit, we'll be checking the next bit. So after that, after adding all this, we'll be assigning to the ith index, we'll be pre-computing for the ith index, and we'll be assigning the current updated value of every bit to the ith till ith index how many bits are actually present. So this is what the main part is. This is what the pre-computation, how it looks like. So we have pre-computed all the results. Now coming to the queries, we'll be having a k, L1, R1, L2, R2. So the size of the first range will be R1 minus L1 plus 1, and the size of the second one will be R2 minus L2 plus 1, and the count A, this can be the count will be count of first count of elements whose kth bit equals to 1 in the first range will be actually equals to prefix of R1 whose I just want the kth bit minus prefix of till L I want from L1 to R1. So we'll be subtracting R1 minus L1 minus 1. So that is what we are doing, and we are doing for only kth bit since they said only for k, and we'll be doing first the second range. So A and B signifies that A is simply the count of elements whose kth bit equals to 1 in the range 1, and B is the count of elements whose kth bit equals to 1 in the range 2. So previously we have discussed that answer will be A into, this is basically in the first range the kth bit equals to 1 element count into, in the second range the kth element whose bit equals to 0, the kth bit equals to 0, will be multiplying this plus, and in the first range whose kth bit equals to 0 into count of elements whose kth bit equals to 1 in the second range, and will be printing the answer. This is how the code looks like. Thank you.